What's up, guys? Welcome back to Tech Tutor. In this video, we're going to continue part 3 of our Introduction to Operating Systems, Chapter 1. We talked about process management. Process management, again, it's deciding which process are we sending. Uh, Process. What is a process? We talked about it's an active entity. A process needs resources to do its task. And then after a process is done, the resources that it used, the CPU, the memory, that is reclaimed. One-threaded, so one process, the process that runs out, has a single-threaded process, right? That runs, has a program counter. It specifies the location of next instruction to execute. Process executes instructions sequentially, one at a time until completion. But multi-threaded processes, they have one program counter per thread. So processes that have multiple, right? They do two or three things at the same time. So a system, yeah, as I showed in the task manager, it has many processes, some users, some OS running concurrently on one or more CPUs. Concurrency by multiplexing the CPUs among the again, concurrency means you run at the same time, right? Process management activities, again, so like creating these processes, deleting these processes, suspending them, providing some mechanisms to process the sync that happens between these processes, the communication that happens between the process and the CPU, the deadlock handling. Say the timer gets over, what do you do then? Right, interrupt is signaled to the process. Another key component that we come across is memory management. Memory management, what it does is to execute a program or uh, we all or a part of the instructions. It must be in memory. So, but all of the data that is needed by the program, that must be all or part of that must also be in the memory. Memory management, what it does, it determines what is in memory. Is it everything, or like how much, right? Uh, while you're putting all that data or that the program, are we utilizing CPU as it should, right? Are we utilizing it as much as we can? And what it does, it keeps track of which parts of the memory are currently being used and by whom. It decides which processes and data to move into and out of memory, allocates and deallocates memory space as needed. Okay, so that's memory management. Primarily works with memory. File system management. So we talked about process management. What else? Process management, memory management, file system management. Process, memory, file. File system management. So the OS, it provides a logical view of the storage, right? There's something we see our folders, we see our files, right? Where is that actually stored, right? It is controlled by this abstracted view. We don't really see where that is stored, right? Each medium is controlled by a device, a disk drive, a tape drive, varying across access speed, capacity, data transfer rate, access method. File system management, what does that do? That helps with organizing the files into directories. Access control on most systems to determine who can access what. OS activities, they include creating, deleting files and directories. Right? We see the interface. We see those yellow folders. But what really happens in the background? Right? What helps us delete? You add a folder. Load this 5 GB folder into desktop. Right? That is what file system management does. Mass storage management. So usually disks, when we have a large data, right? How are we going to store that? All right. How are we going to how do we make sure the computer doesn't crash? So mounting and unmounting this data, freeing space as needed, allocating the storage probably in chunks, right? Disk scheduling, partitioning, protection are all things that the OS does. And we mentioned about caching in the last video. Caching is an important principle, right? What it does is it helps in using it's copied from slower to faster storage temporarily. So store things in the secondary storage, as we talked in the previous video, secondary and tertiary storage. If you want to use that, you move that into main memory. if you want for faster storage, right? You cache it. You don't remove it entirely, right? You take chunks of it and you directly access it so that you can access it fast. Uh, it's moved to this cache, right? Temporary storage. Smaller than storage being cache management. It is an important design problem that we see. It also has a size and replacement policy. And then we have various types of storage, as you can see. Like we saw that level, right, where this is the fastest, right? When we go slower as you go this way, but this is the safest, and it gets unsafe, right? Volatile, non-volatile. Registers, cache, main memory, solid state disk. As you can see, the size really increases, right? You get to 10 terabytes on a magnetic disk. Um, Coming to how we would want to migrate data from a disk to a register, right? So when we talk about a disk, right? So this could be what happens? This could be again a CD drive or a large storage device, right? And then how do we get that storage, right? How do we move it into something that we could read? We move it from the magnetic disk to the main memory where it is cached, okay? And then that cache to read that cache, you have that register, that hardware register. Multiprocessor environments, they must provide cache coherency in hardware such that all CPUs have the most recent value in their cache. And distributed environment situations are even more complex where you have multiple environments, right? Not just magnetic disks. Where you have probably not just one, right? Probably two or three magnetic disks. How are we going to load it? So data when several copies of data must exist, and then that's something we want to look also in later chapters. Moving next, input output subsystem. Again, talking about input output, and it's another big topic that we come across in operating systems. How input output is done on a computer, a phone, right? Buffering, storing data temporarily while it is being transferred, caching, storing parts of data in faster storage, like as we've seen, where for, for performance, spooling, the overlapping of output of one job with input of other jobs. Yeah, so again, understanding the difference between buffering and caching is also important. So in this, you are storing the data like temporarily while it is being transferred, uh, but then caching is you're storing the parts of the data in faster storage for performance. The storage itself is meant to be fast, temporarily, right? Protection and security, another key component. Protection means any mechanism for controlling access of processes or users to resources defined by the operating system. Security, it's the defense of a system against internal and external attacks. There's a huge range, including denial of service things if you've done cybersecurity things really before, worms, viruses that could be, done on these or OSS operating systems. So systems when they distinguish between users, right? User IDs. So the level of permissions that user has, right? What are they in a group ID? Are they do they have root admin privileges or normal privileges? Moving on to virtualization. What is virtualization? So this allows the applications OS to run applications with other OS. If you've done cybersecurity, this is something you might have come across before, like having probably like Ubuntu or Kali Linux or another operating system inside a bigger one. For example, Windows. Last semester, I had to take a class where I had to use Kali Linux inside my Windows system. So virtualization is that feature that helps you do that. You don't have to have the entire OS, um, and the OS itself, it's compiled for CPU, right? The guest OSs are also natively compiled. So have a look at VMware, VirtualBox. They all are virtual machine managers that to help provide virtualization services. Again, it's used for running multiple OSs in a large in an OS. For example, after the laptop running Mac OS, a Windows machine having Kali Linux, and so forth. Computing environments, if we look at it in the case of virtualization, what they look like. This figure, as you can see, this is This shows there's a hardware layer, then there's a kernel layer where there's these processes. But then when you can have multiple VMs, right? You can have multiple um, OSs, right? You have processes for this virtual machine, processes for this virtual machine, and you have a virtual machine manager that's that's an added layer. Distributed systems, so multiple different types of systems that are networked together. Networking is another important component of operating systems. Whether something that a device you're putting, is it on the LAN, or is it on the wide area network, or is it on the MAN or the PAN? LAN and WAN are the most common that you will see. My computer right now, it's kind of done on local area network with the router downstairs, right? So network operating system provides features between systems across networks. The scheme allows systems to exchange messages. And yeah, so coming to the architecture of that we've seen also, some we've seen in previous slides also. Computer system architecture. Most systems use a single general purpose processor. Nowadays we have multi-processors, that you can run parallel systems that are tightly coupled, right? You could increase throughput, economy of scale, reliability, and when you think about these two types under this, you have asymmetric and you have symmetric. Asymmetric means each processor is assigned a specific task. Symmetric means each processor performs all tasks. Okay, so symmetric, you have you have these tasks and it performs all of them at once. But asymmetric, each processor is assigned a specific task. Symmetric multiprocessing, as you can see, so you have this processor, and and then you have two processors, right? And they have a CPU for each of them. Coming to multi-chip and multi-core, chip can contain multiple cores. And as you can see, this contains multiple separate systems, right? CPU core, CPU core. Then you have a cache over here. Now, non-uniform memory access system, and in this you can see there's multiple CPUs, and those CPUs are connected. And in a way, they have access to the different memory sources also, instead of just one. So you see this web that starts forming. Going to clustered systems. So we talked about single, right? We talked about single processing, multi-processing. Now another type is clustered system. Clustered systems, you usually would see in a high performance cluster, like where you're running these high performance, like GPUs, NVIDIA GPUs, mainframe computers. When you have to request some resources, right, for a specific time, this is an example of a clustered systems. Where you have a distributed lock manager to schedule, and to avoid two processes, merging into each other. So they're usually storage via storage area network, SAN. There's two types: as asymmetric clustering, where one machine is in hot standby mode, where it's for a specific task, right? But symmetric clustering has multiple nodes running applications monitoring each other, right? Not instead of just one application. Cluster system, this is what it kind of looks like. You have this network that's connecting each of them. Then you have different computers, multiple computers. Example of a motherboard. Moving forward, computer system environments. We have multiple types of computing environments, like traditional, mobile, client server, peer-to-peer. Let's talk about them in detail. Traditional systems, they're standalone, like they connect with each other. They have portals for web access to internal systems. They're like web terminals, and they interconnect via wireless networks. Mobile systems are mobile phones, right? They also have an OS. Our modern day phones, you have a GPS, gyroscope. There's so many things with it, right? You have the new types like augmented reality, right? So if you look at it, a phone today is much powerful than what a laptop is, and that's why that explains why some phones are, like an iPhone is expensive than a laptop. A phone is expensive than a laptop for these features that it brings along, right? And if we look at a client server model, It looks like we're running out of time. We'll talk in the next part. See you guys. Thank you for sticking around. See you in the next video.